Hey everyone, so today we're going to compare two different sorting algorithms, Quicksort and Mergesort. One of the prerequisites for this lecture is that you should know how both of these sorting algorithms actually work, so that it will make you understand those differences in a much more clearer fashion. So let's get started. First of all, why do we need to learn about different sorting techniques? Every programming language that you use already has a built-in sort which you can use to sort your containers. So why do we need to learn about different sorting techniques? Right? So one of the main reasons for doing that is you get to understand several problem solving techniques which can be used not just in the case of sorting but also within other areas of computer science. So quicksort and mergesort use something called the divide and conquer strategy, which can be used in other areas of computer science, like suppose finding closest pair of points in a plane, for example. Right? Also, one of the other things that you learn is you actually are able to identify which set of algorithms or problem solving techniques would perform better under certain scenarios. So here your state is getting transitioned from an unsorted container to a sorted container, right? And different algorithms actually achieve that using different time and space complexities. So you understand how different algorithms perform under certain scenarios, right? So to start the comparison, let's just see how the pseudocode for Quicksort and Mergesort is and how does it perform. Then we can actually move towards the comparisons. So let's start with Quicksort first, and I'll assume that you guys have some idea about how these algorithms work, right? So what are we doing? We're taking an input array, and start and end is the start and end positions of this input array, right? So what we try to do is we try to partition this input array around an element such that all the elements lesser than that element lie towards the left of the array, and all the elements which are greater than that particular element lie to the right of the array. So that element is called the pivot element, right? So this is the left half, this is the right half, right? So what we do is we partition this array around this pivot element, right? Now the pivot is at its correct position in the sorted order. Now we apply the same technique recursively to both the left half and the right half, right? So what do we do in the case of merge sort? So in the case of merge sort, we actually divide our input array into two equal halves, both of size. Suppose the input is of size n. So you divide your input into two equal halves, which is of size n by 1 and by 2. Now once you have divided this into two equal halves, you sort both of these halves individually, and then you apply the merge step, right? So if you assume that this A is actually an array, right? So how do we actually merge it? We use a temporary array of size equal to n, and we actually merge both of these sorted halves to create a total sorted half of size n, right? So once we have done that, we copy this sorted half to the original array. I hope that you guys already have some idea about how these algorithms work, so I'm just going through over it quickly, right? So now, since we are actually using an auxiliary space here, right, at each step, the space complexity for merge sort comes out to be O of n, where n is the size of the input array, because in the maximum case you would actually create a temporary array which is of size n, right? Now let's suppose what is the time complexity for this, right? So at each particular point you are actually dividing your input into two equal halves, right? And then you divide it into again two equal halves recursively. So what is the depth of this recursive stack? The depth of this recursive stack is actually log n to the base 2, right? And at each recursive step you are actually performing the merge step, which takes what time? Which takes a time of, in the worst case, O of n, right? So the time complexity for merge sort comes out to be O of n log n, right? So this is the time complexity, and this is the space complexity. This is worst case time complexity and the space complexity for merge sort, right? Now let's analyze Quicksort again, right? So basically what we're trying to do is we're trying to partition our array using this pivot element, right? Let's suppose in the perfect scenario we consider the best case first. In the best case, suppose this pivot element actually divides your input array into two equal halves, which is of size n by 2 and n by 2, just like in the case of Mergesort, right? And recursively also, when you choose a pivot for the left half and the right half, those pivots also divide your left half and right half again into two equal halves, just like Mergesort is doing recursively for all the partitions, right? In that case, what will be the time complexity of Quicksort? The time complexity of Quicksort in the best case, where it's dividing into two equal halves every time recursively, would be similar to the time complexity of Mergesort, which will be what? O of n log n, right? And what will be the space complexity? Since we already know that in the partition technique, we are not actually using an extra space, we are doing it in place, right? So the space complexity would be what? The depth of the recursion stack, right? So what will that be? So that will be what? That will be log n to the base 2, right? So this is the best case performance of Quicksort, right? Now let's see what would be the worst case performance of Quicksort. Yeah, so let's just try to see what actually leads to the worst case scenario of Quicksort, right? So we have already talked about how we choose the partition element and partition our array into left and right arrays, right? Let's suppose the partition that you chose always lied towards the start of the array, right? Now all the n minus 1, suppose the size is n, so all the n minus 1 elements would lie to the right of the partition, right? Right? Let's suppose again recursively also, the next time you choose a pivot, it again lies to the start of the array. So what will be the number of elements to the right of the partition? That would be what? N minus 2, right? And it goes on. Basically, we are getting very unfortunate while choosing the pivot location. It is not dividing your array in actually two equal halves, but it's actually dividing your array in a very skewed fashion, where all the actual elements are lying towards the right of the pivots, right? So in that case, what will be the height of this recursion tree that you get? That will be what? N, basically, right? And each time you do a partition, what is the time complexity of the partition each time you do it, right? The time complexity for that partition is also n, right? So what is the time complexity, worst case time complexity that you achieve? So that will be what? O of n square, right? And the space that you are using would be the depth of this recursion stack, which will be what? O of n, right? Now basically this particular space can be optimized using something called as a tail call optimization for Quicksort, which actually reduces this space taken by the recursive stack to O, from O of n to O of log n, right? Now this particular optimization is out of scope for this lecture. We'll cover this in a separate video, right? So now that we have analyzed the space and time complexity for both of the algorithms, let's just move on towards which scenario would be preferred for each sorting algorithm. So we had seen the worst case time complexity for Quicksort as well as Mergesort. For Quicksort it is O of n square, while for Mergesort it is O of n log n. So and the space complexity used by Mergesort is actually O of n, which is because we use a temporary space or an auxiliary space when we do the merge step in each recursive call, right? And the space complexity used by Quicksort is actually O of log n, which is achieved by a tail call optimization, right? So when did we achieve the worst case? How can we achieve the worst case of n square in Quicksort? Suppose your array element is already sorted, right? So and if you are already always choosing the first element as the pivot, right? In that case, your partition would be very skewed. So suppose if you take the first element as a pivot, then how all the elements would actually lie to the right of the pivot, right? And then the left half would have nothing, right? Again, recursively, if you choose the first element as the pivot, again the same thing would happen. The right half would have all the remaining elements, and the left half would have nothing. So this would actually lead to a time complexity of O of n square, as we had discussed already, right? Now how can we improve that? we can improve this by using something called as a randomized pivot, right? So if we choose a random element out of these as the pivot element, then we can reach a time complexity of O of n log n, which is the average case, right? The worst case still remains the same, right? So we can see from the time and space complexity analysis that in terms of the worst case time complexity, Mergesort actually performs much better than Quicksort, right? But the space used by Mergesort is actually equivalent to the input array size, while that used by Quicksort is actually much lesser. So we need to see in what scenarios would you prefer Quicksort over Mergesort, and in what scenarios would Mergesort be preferred over Quicksort. So to understand that, we need to first understand another term which is known as locality of preference. Let's start with this. So before moving on to scenarios, let's just talk about this term, locality of preference. And we'll not go into too much detail about this, but we'll talk about why it's relevant for our discussion of these two sorting algorithms, right? So what exactly is locality of preference? Locality of preference is the tendency of the processor to actually access the same memory block over a short period of time. So what does that mean basically? Suppose this is your main memory, right? And it is divided into blocks, right? Now, suppose this is your cache memory, right? So if your block is actually accessed quite frequently, what the processor will do is will put this particular block into this cache. So next time it has to access elements within the block, it will actually first look whether those elements are present in the cache, and most of the time that would be a hit because we are putting the frequently accessed blocks in the cache, right? So why is this relevant for our discussion, right? So what if you see, if you consider this container which is A, and you think about this container as an array, right? So what is special about an array, right? So array has sequential memory locations, right? So suppose this memory location is X, this would be X plus 1, this would be X plus 2, this would be X plus 3, right? Now when we actually do the partition step in Quicksort, what we are actually doing is we are choosing a randomized pivot first, and then we are scanning the array and we are seeing which elements are less than or greater than the pivot, right? So when we are scanning the array, so we are actually scanning sequential elements, and those sequential elements are actually likely to be present in the same block. And since this is done recursively, we are actually doing this quite frequently. So what will happen is the processor will actually move those particular blocks of array elements to the cache, right? So the free access time taken by the processor would be actually much less because it is fetching from cache rather than from main memory. So we can say that Quicksort has great locality of preference, right? Now let's see what happens in the case of Mergesort. So what happens in the case of Mergesort is we actually have two sorted halves, and we put the elements from these sorted halves into a temporary container, right? So how are we moving? We are accessing these halves using some pointers. This is the left pointer which is here, and we can call this the right pointer, right? And each time we compare the left and right pointer and we see which one is smaller, and we put that in the temporary array, right? So which is of size n basically in this case, right? So as you can see, the array elements that are accessed are from simultaneously from the left half as well as from the right half, right? Even though there is some locality of preference because we are actually scanning this right pointer, but we are simultaneously fetching from two different halves of the array. So that is why Mergesort is not said to have great locality of preference. It has poor locality of preference, right? And why does this bother us? Let's suppose we are actually sorting arrays, right? We know that the average case time complexity for Quicksort is actually O of n log n, right? This is the average case, right? And the worst case is O of n square, while the worst case for Mergesort is actually O of n log n. But we have to consider that Mergesort actually uses much more space, which is equivalent to the size of the array. and we can easily avoid this worst case time complexity of quicksort using a randomized pivot. So what we would do is we would prefer to use quicksort in case of arrays because of the great locality of reference that quicksort provides. Let's see one more example where mergesort would actually be preferred. So we had seen when the this particular container was in array that Quicksort was able to exercise its great locality of reference to actually perform better in the case of arrays. Let's suppose we have another container which is something like a linked list, and we have to sort this linked list. Right, so we no longer have an array. So what is the difference between the linked list and an array? So the main difference is that the memory locations in a linked list are not actually sequential, right? So Quicksort would not be able to exercise its good locality of reference over linked list, right? Now what will happen in the case of mergesort? Let's see. So in the case of mergesort, suppose we have these two sorted halves and these could be of any length, right? Probably equal lengths, right? Now we need to create, we need to do the merge step for both of these halves. Now, in the case of linked list, do we need an extra space for merge step? No, we don't. And why is the reason for that? Basically, suppose this is the left pointer and this is the right pointer, right? If you take this particular element, if you compare both of these elements and you take this particular element in the merge step as the first element, if you have to take the next element, you don't have to actually do any sort of rearrangement as in the case of array, right? You just need to change this particular link which is now pointing to this. Suppose this and this will now be compared because we have taken the left pointer, right? So now this is the current pointer and we compare current and the right pointer. Suppose this right pointer is smaller, right? So what we'll do is we'll take this right pointer and we'll point this originally taken node to this pointer, right? So we are actually just rearranging the links to form the sorted list, right? So in this case, we didn't actually utilize any extra space. So in the case of linked list, mergesort would be the preferred way to go since it provides a worst case time complexity of n log n and we are not using any space, right? So for mergesort, for linked list, mergesort would be the preferred way, right? So we have seen certain scenarios where one of the sorting algorithms will be preferred over the other, right? So I hope that you are able to understand the algorithms in a much better fashion now. Thanks.